Hi there, welcome to our channel where we talk about traffic operations in practice. The overall intent of this video series is to reduce the learning curve for students and entry-level engineers by providing them free and high-quality learning materials in the field of traffic operations, including highway safety and travel demand modeling. The majority of content in this work is written by Professor Jiangling. My name is Amit Kumar Singh. I'm one of the contributor of this work. I'm a licensed engineer in the state of Texas. I received my bachelor's from IIT Bombay in India and my master's from UT Austin in US. Other three contributors of this work are Priyanshu Singh, who works in the field of artificial intelligence, Nidhi Kumari, who has a background in computer science and is a programmer, and Namrata Kumari. She has a background in electrical engineering and currently she is working as data scientist. Now let's get to the main content. In this video, we will discuss the gravity model for the trip distribution and wrap up the trip distribution, and then we will look at the mode choice. Before moving forward, let's recap what we have learned so far in previous videos. So in previous videos, we know that in step 1 of 4-step travel demand model, production attraction table is generated, and this production attraction table is sent to trip distribution stage where there are infinite set of solutions that are available that will match the production attraction. Now, based on if a reliable base OD is available, let's call it base OD. If a reliable base OD is available, then we can use something called growth factor method, which we have seen in previous videos. A growth factor method utilizes the base ODs and tries to match the PA table using 4 different methods we looked at along with the examples. And then it tries to pick one of the ODs out of infinite solutions that are closely related to base ODs. Now, if the base ODs are not available, which is most of the TDM models, so for majority of TDM model, this base OD needs to be synthesized. So when a reliable, this needs to be a reliable base OD matrix is not available, then a base OD matrix needs to be synthesized. It's also called synthesized OD. The trip between each origin and destination pair from the PA table are typically distributed using a model known as gravity model. The name gravity comes from its similarity compared to Newton's gravity model. So Newton's gravity model is gravitational force. If I remember my uh, pre-high school correctly, is a universal constant, mass 1, mass 2 divided by r square. So this is Newton's gravity model and kind of what we use for the trip gravity model. So trip between origin I and destination j is given by a constant similar to this one. Production of I, so uh, number of trips produced from zone I, and then attraction of no zone j, and then instead of r square, what we have is called impedance function. So we have an entire function here, and this is called if I'm looking here correctly, is called impedance factor, which is usually like either a factor or a function. So because of similarity to Newton's model, is called gravity model. So in most of the TDM model, gravity model is used instead of growth factor method. So gravity model simplifies things in TDM model and is used in most of the 4-step travel demand models. So the gravity model can be written like this, where 1 divided by impedance factor can be written as interaction factor between zone I and zone j. So more the production of zone I, the more attractive it will be, and more the attraction of zone j, there will be more trips, and then the impedance inverse of impedance factor is called interaction factor. It's just some terminologies. We don't need to remember these things. The impedance factor is what we are taught in school, so it's kind of just to remember here, but it's not widely used term in practice. Then this proportionality constant can be determined by summing of Tij. If we sum it with respect to I, then we will get Aj, and if we sum it with respect to J, we will get Pi. So since we are summing it up with respect to J, sum of all Ti's is equal to Aj, then we can calculate this K. K can be calculated as 1 divided by sum over all the J's, Aj, Fij, and then that's what is written here. So here in this last part, the proportionality constant has been replaced by using these fundamental equations of trips. So trips between origin I and destination J is given by this formula. This is called gravity model. Again, this is not a single number which is accurate. There are infinite set of solutions, and this is just one of the assumptions that two trips between origin, let's say origin 1 and destination, let's say 11, will be dependent on the impedance factor. So that's the assumption here, and based on this assumption we are trying to select one of the infinite set of solutions. So we are trying to select one of the infinite set of solutions based on this assumption. In practice, is written here, there are several nuances in travel behavior and transportation system that cannot be accurately modeled with a standard gravity model. Hence, a K factor is often used to adjust the trips in order to account for nuances in this travel behavior. So what we do is for each trip between origin and destination, let's say Tij, we have a calibration factor called Kij. This Kij is different than this constant here. So this Kij is calibration factor for each trip to account for nuances in travel demand model that cannot be captured in based on gravity model. So gravity model kind of uses just one parameter, which is called impedance function. Anything out of impedance factor that affects the trip distribution, there can be thousands of other variables, and actually is gravity model is pretty good, but still it lacks the accuracy to predict correct OD pattern. So the gravity model is completely based on impedance factor and production attraction kind of proportionality. However, not everything is captured within gravity model. To calibrate the uncaptured or unknown kind of variables, we use this calibration called Kij. Please note that K factor here is different than proportionality constant. K factors are often applied at the district or jurisdiction level to adjust regional distribution patterns and may be applied for trip purposes or all trip purposes. And we will look into how the K factors are calculated and applied in the later sections when we look at the Kij in more depth. So base OD matrix estimation using gravity model is usually unbalanced. So out of gravity model, what we end up getting is a new OD matrix. So this is a OD matrix where each element is given by this equation. So each element is given by this equation, and that's the gravity model. So once we get the gravity model, since we have balanced it out based on production by summing up all the attraction, the productions are usually always balanced, but attractions are not balanced. Then we can use one of the earlier four methods to balance the attractions and productions at the same time. So let's look at one example. So here we have three zones. This is the future production attraction table for the future 16, 28, 40, 30, 16, 38. It seems like it's the same as the one example we used earlier. Yes, it's the same numbers as the one we used earlier. So we are carrying forward that example where we had this PA table, And in earlier example, we had the PA table and we have the base OD matrix. But instead of base OD matrix, what we have now is move a little bit up. We have friction factors. So friction factors can be calculated. Friction factor, we'll look at what are friction factors just a little bit down. Uh, Here we have a calibration of gravity model, and here we are discussing the friction factor. So we will see how this matrix comes. So let's say this is our friction factor, or let's call it interaction factor. And we are trying to determine the future OD table so that it matches this and is based on this friction table. So the first step will be to calculate each element of the future OD based on this equation. So I will show this example in Excel. Here what I have done is on the right hand side I have put the production here, attraction here, friction factor here, and I have used the formula given here. So the first number is this production multiplied by this attraction, and if I scroll it little bit towards the right, multiplied by this friction factor divided by sum product of this friction factor multiplied by this attraction number. So for this one I have repeated the attraction to facilitate the sum product. In the second one, what we will do is we'll pick the second number. We'll notice here in the second one we have this second number selected. In the third row we will have this third number used twice. So this is how we can calculate each element of the OD. So for the second attraction, we'll notice 16 is in use. For this one, let me skip. And for this calculation, going from zone 2 to zone 3, we'll notice the zone 3 is in play. So after using the formula, this one in Excel, we can calculate this first matrix. This is based on gravity model. We will notice that all the productions are already balanced because we are using the attractions to balance them out. And then we have unbalanced attractions, and then we can use one of the four methods to balance them out. So here the example asks to use furnace method to balance them out within 5% error. So we have went through furnace method in previous example. So what I'm doing is I'm multiplying first by EIs and then balancing them out, then I'm multiplying by EJ, then balancing them out, and so forth. So then it kind of converges to these numbers. 6.2, 5.86, which is here, converges to these numbers, and these are within the acceptable error threshold. So this is how gravity model works. Instead of base OD, what we have done is we have synthesized an OD. We have developed OD by ourselves. So this is called synthesis OD. And what we have done is from previous examples, we had base OD. So we have threw away base OD and we have synthesized OD based on some friction factor matrix. So next we will look at what is this friction factor matrix. Calibration of gravity model. The impedance factor is a function of generalized cost that is determined using known data sets. Typically, impedance values are set equal to generalized cost. So higher the cost between two origin destination, the lower the number of trips will be. So let's say this generalized cost includes travel time. So generalized cost includes the travel time between them. If there are toll road, then some toll cost, distance, because the fuel is burned based on distance, so we might consider distance or many other factors to come up with an equivalent cost between each OD pair. So let's say this is origin number 1, destination 2, destination 3, destination 4. Then we figure out what is the generalized cost to go from these to go 3 different destinations. And then based on the generalized cost, we calculate the impedance value, and 1 over the impedance is gives us friction factor. So after impedance factors are set based on the bigger database, so what we do is we do not go and calculate uh, the generalized cost one by one. What we do is we have the OD trip pattern for existing, and we try to estimate it based on the larger data set we know. So after impedance factors are calculated based on the known data set, the K values are calibrated. So the K value accounts for variables that influence the trip distribution but are not captured by standard gravity model, like we discussed just a few minutes ago. So first, the impedance factor is calculated based on generalized cost. Impedance factor based on generalized cost. Based on impedance factor, 1 over impedance factor gives us the friction factor. And we use the large data set to estimate this instead of going and trying to figuring it out one by one. And then after this work is done, then we go and use the large data set to figure out the calibration factors. Advantages of gravity model: the both limitations of growth factor method is resolved in gravity model. The first limitation was the growth factor method is based on base OD, and it does not capture the future transportation network and future developments properly, whereas gravity model explicitly cover them by use of generalized cost and travel time. So let's say in future uh, there are new roadways that are going to pass, and the travel time on this roadway can be estimated using certain functions we will see. So based on the travel time, travel cost we are expecting, we can figure out we can account for the transportation changes that are going to happen in future to calculate the new travel time, new generalized cost, and then account them to generate the impedance matrix. So the impedance matrix is based on future socioeconomic data and future roadway network. So once we have the future impedance matrix based on future network, which is directly accounted in the impedance matrix, we can calculate the new trip pattern. So the gravity model can account for transportation system improvement through the use of impedance factor. If the generalized cost between two zones is expected to decrease in future, then accordingly according to the gravity model, the number of trips between two zones would increase. So let's say there is going to be a new freeway which is going to reduce the number of reduce the travel time. Hence the impedance is reduced and the friction factor increases. So let's say one zone is here, one zone is here. So in future, the trip between these two origin destination will likely increase because of this roadway improvement, and is directly captured using this impedance factor. Whereas in growth factor method, what we have is base OD, which is based on existing ODs. So in existing, if there are less vehicles going between these two, most likely in the base OD, this number will be low and we will end up with a low number. So gravity model is kind of heavily used over growth factor method because the base OD is kind of difficult to calibrate for the future scenarios. So we use the gravity model to figure out the impact of the improvements on the travel pattern changes. And unlike growth factor method, the gravity model can easily provide non-zero trips based on future conditions. So let's say in existing development, there is nothing here in this zone and there is nothing here in this zone. So the trips between these two in existing may be zero. And in gravity model, even if in the gravity model, even if this location has many developments in the future, and this location also has many developments in the future, these trips will always be zero based on gravity model, except the optimization method. Whereas in the trips will always be zero using growth factor method, except for optimization method. Whereas in gravity model, since it's based on the impedance factor, this number of trips can be non-zero. as the base trip uh, the base trip is not a factor in the gravity model. So this will be, if there are more developments here and more developments here, then the number of trips between these two zones will be not only non-zero, it will be high, because it dependent on production, attraction, and the friction factors. So gravity model overcomes both of the limitation of growth factor method. That doesn't mean gravity model is a perfect model. There are some limitations to it. A destination is chosen primarily based on zone attraction and impedance factor. However, majority of destination choices are made based on the need of individual household. So this is a big approximation where we are trying to choose the destination based on how attractive certain zones are, but probably is one best thing we can do uh, under four-step travel demand model. Otherwise, we can look at the base OD and try to combine it with the gravity model. The second limitation is impedance factor and K factor are kept same between existing and future year, which may not hold true. So here the impedance function itself, not the number. So let's say impedance function is using a linear line, so the impedance function may change in future. So let's say the toll cost is $3 per mile, it might increase or decrease in future. So impedance factors are kind of kept same uh, between the existing and future years. That may not hold true. So it's kind of a small uh, kind of limitation, but another limitation is the calibration of K factor. So the calibration is carrying forward as it is. So existing calibration is transferred to the future gravity models, which may not hold true. So far we have looked into trip generation and trip distribution. Now let's look at the step 3, mode choice. So we started with figuring out how many trips will be generated in PA table. Then we end up with OD table by each trip purpose. So let's say this is home-based work and this is the OD table. Now for each OD, each element of the OD, there are different modes available. So some of the modes are listed here. So there is walk, bike, car, transit, share vehicles, rental car, aviation, etc. Now drivers or a person can travel between the ODs using different modes, and the mode they are going to choose depends on how good the public transportation is, what are their income levels, and several other things. So this is called mode choice. The mode choice presented here is kind of rarely used in practice. It's just used within the TDM model. However, the choice models, we are not talking specifically about the mode choice, which is related to transportation engineering. The choice models are widely used in engineering, advertisement, marketing, and business analytics to analyze people's choices. So choice models which look similar to this are heavily used in different kind of industries. So this mode choice or the choice models are kind of well researched, and there are, I would say, thousands of paper on different kind of choice model, the different kind of regressions, different kind of error assumptions, and many other things. So this is one of the heavily researched topic outside of transportation, or even within the transportation. When the research paper are written based on survey data, most of them use a certain kind of choice models. So we will not go in that much depth. Those are out of scope of this book. We are only focusing on mode choice, but just kind of wanted to mention that this is heavily used in other practices, and especially in survey based research papers. So probability of choosing a mode I is given by e to the power utility of mode I divided by sum of all the utilities. So this is called logit model, multinomial logit model, and utility function is given by this. We can estimate the coefficient of these numbers using different softwares. So x is the independent variables influencing the, and these are dependent variables. So influencing factor can include time, cost, access, convenience, societal perception, safety, etc. So all these variables goes towards the utility of a mode, which is then fed to the multinomial logic model in most of the TDM models. But there are many other models, like a probit model. There are many other models which can be used for choice models. So if you are in academia, you will be playing around with these models a lot. So many other choice models are used in practice, such as multinomial logic, multinomial probit, order logic, order probit, nested logic, nested probit. Discussion of this model is out of this scope of this book, and they are not used in practice, or at least I have not seen them outside of research papers. I have seen them in many research papers, but not in practice.